going to share the screen. Visible?
Yes, visible.
Okay. So let's go to the previous offering of the course and let's go to week 2 assignment. And all right, so there are 1, 2, 3, 4, 5, 6, 7, 8 questions. So I think we can cover them in slightly more than 1 hour. Okay, so I will let you read the first question. So this is about the feedback vertex set. Okay, so what is a feedback vertex set? So a feedback vertex set is a subset of the vertices in a graph whose removal uh, will break all cycles. So that once you remove these vertices, then you are left with a forest. There are no cycles in the graph. So that is the definition of feedback vertex set.
Yes.
So
So
yeah, go ahead.
what this V3K here is, and moreover, what are the reduction rules?
Oh, just a second. Right. Yeah, so the reduction rules. I'll have to define the reduction rules. So you can understand that. Let me also look at it at the same time. So you've been given a graph, and the question is, can you remove 3 vertices and of course the incident edges so that all the cycles are destroyed? And to do so, as usual, there's some kernelization rules, reduction rules, and after applying these reduction rules exhaustively, then you are left with what is called a reduced graph, and its minimum degree is at least 3, that is from the video. And then there is a technical lemma which says that any k means three sized feedback vertex set contains at least one vertex of, so 3 v sub 3k is a subset of the vertices. So how many vertices? 3 into k, that means 9 vertices. So any 3 sized feedback vertex set should contain at least one vertex from this set v3k containing 9 vertices. So the question is, what is this set of 3k vertices? So first we have to be mechanical and apply these rules. So first let us see what are the rules. My pencil is out of charge. Let's wait for a Let us say 30 seconds. Let the pencil get charged. So let me copy this diagram. So we are going to apply these four rules on this graph. So let's open the whiteboard and first copy the graph. So there are a couple of reduction rules. One of the rule is remove the vertices of degree 1. Okay. Identify the vertices of degree 1. So one of the rules is okay. Another rule is remove vertices of degree 2 and add an edge joining the two neighbors. Neighbors of the removed vertex. Okay. So after that, after that the other reduction rules are not applicable. Also, I don't recall the other reduction rules. So after that, we will be getting what is called the reduced graph. And in this reduced graph, we want to identify that what is that subset V3K of the vertex set, and how to obtain that subset is also defined. So that is done by sort the vertices of the reduced graph in decreasing order of their degrees and output the first 3K vertices. Okay, so the other thing you do is on the reduced graph. So what you will do is sort the vertices of the reduced graph in descending order of their degrees. Then the first 3K vertices forms V3K. So output first 3K vertices. So that's all we will do in this question. Okay, so let us apply, let's call this. Okay, so according to the video, this is rule 3. And this is rule 4. I don't know what is rule 1 and 2. I don't recall, but the rule 1 and 2 are not applicable. So shall we apply rule 3? So which are the degree 1 vertices?
Yes, so E, B, M, and N, these are the only four vertices of the degree 1.
So let us delete these guys.
Yes.
Okay.
And S and F, are the only two vertices of the degree 2. So yeah, so we need to add an edge joining the neighbors of the removed vertices. So neighbors of S are I think K and then T. So K and T will get connected, and and P and G will get connected. So in short, the degree of P and G will get increased by one, and the uh, degree of S has been removed. So degree of K and T is also increased by one.
Correct, correct. So you have identified correctly those vertices having degree 2. Now, once they are deleted, the incident edges are also deleted, but the two neighbors will get an edge. So let's draw an edge. Let me use blue color. So the J and P are neighbors to I, so they got connected. And C and T are neighbors to S, they got connected. Again, C and G are neighbors to F, so they also got connected. Okay, so now we will count the degree for each vertex. In fact, we want to uh, sort them in decreasing order.
So this figure is very, very complicated. And then to count the degrees of all the vertices.
So let's identify the largest degree vertex. So
Yeah, so that is D. D vertex is having the largest degree.
okay, so D is largest degree. So we'll say what is the degree of D? We'll just make a table. So D is, let us say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So T's degree is 14. We want to identify only the top 9. Oh, this is a cumbersome question.
Yes. And after this D, we can think of C, and the degree of C is 1, 2, 3, and 1, 4, 5, 6, 7, 8, 8 something, 8 or 9. The degree of the vertex C.
Okay, so 1, 2, 3, 4, 5, 6, 7,
Uh,
8, 9. I see 9. But oh, so this guy got deleted. You have to remember that this guy got deleted. So yeah, it remains 8. This edge that was connecting C to S got deleted. So C1 will count 8. Okay, what
yes.
is next?
So
A.
next is A. Yeah.
So A was A connected to some vertex which got deleted? No. So we can count normally. 1, 2, 3, 4, 5, 6, 7.
Yes. Uh, and
Then
after A, it would be uh, either Q or K.
let's
Uh,
take Q. K also. K is 1, 2, 3, 4.
K. So one more. The degree of K uh, will be increased by one because T and K will get connected. So because of the removal. So then the degree of K came out to be 1, 2, 3, 4 plus 1, 5.
No, so K, you are adding one more degree for what reason?
Because K is the neighbor of S, and T is also the neighbor of S. And since S was removed, so therefore the degree of K and T will get increased by 1.
No, so S is a vertex of degree 2, and that is the reason we could apply this rule that remove vertices of degree 2. So K has exactly two neighbors, C and T.
Oh, K is not the neighbor of S. Fine. Yes,
A-
yes, yes.
S is connected to C and
C.
T.
Yes, yes. So K's degree of K is 4 then.
All right.
Yeah, the degree of Q is also 4.
Yes. Let's identify some more 4 degree. This is also 4 degree. After we have added the edge. No, 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 no. This is not 4. So this got deleted. This got deleted. This got deleted. So this is not 4. So is there any other vertex with degree 4?
So for 4, it is P. I think we should focus on the vertex P because P
Okay.
is getting connected to other things. So 1, 2, 3, and then 4. 1, 2, 3, 4, 5. The degree of P is even greater than 4.
Now this two are deleted.
So this we have deleted, but then P is connected to G also because of the rule number 4 somewhere. So P is connected to G, and where is G here? G,
G is
yes,
here.
yes. So P was connected to G because of the removal of F. No, but then P is not the neighbor of F. Sorry. So PG is not okay. But then P and J will get connected, resulting into 1, 2, 3, and then 4. Yeah, so P is 4.
All
And
right.
next,
So P is
there
4.
are many vertices of the degree 3.
No, so how about R?
So regarding R, 1, 2, 3, and then 4. Yes, the degree of R is also 4.
All right. So we have already identified 7 things. How about
Yes.
T? So T had 4 neighbors, but one of them got disconnected. But then additionally, T got connected to C.
Yes. 4. T is also 4.
All right. So what are we left with? We have we counted J?
So regarding J, so one was removed, but then one was added. 1, 2, 3, 4. J is also 4.
Fine. So we have identified already 9 vertices. And so these are the, so after that, all the vertices have degree 3 or less. So we should be satisfied that these are the top high degree vertices. I mean, top 9 high degree vertices. We're only interested in them. So this is the set. Let us see what is the example. What are the options? Oh, let me copy this first. So this is what we have. Let's recall this. So we have BCAQK in our solution. Okay, so let us see the options again. Can I copy the options?
So all the DCAK is, but we are having DCAQK, it's okay. After then K, we can have, because all these values are 4. Can we see that after which value the values are same because they won't be in the same order here in the answer?
Yes.
So after DCA, all values are 4. Yeah.
We have to focus on these
Yes. So the order may be
PQR, TJK. So
yes,
JK, PQR, and T.
yes. I've noted down these values.
Great. So PQR, JT, that's the first question answer. So answer accepted answer is also A. Uh,
KJ, KJ, PQRT, Yes, correct. Yeah, right.
Okay. So actually,
So,
go ahead.
yeah, please continue. Yeah.
Actually, it's a very video specific question that you have to do this, then only you get the answer. It's not a generic question. Anyway,
Yes. So, what is the relation in between this vertex cover popular problem and this lesser known feedback vertex set? Uh,
So feedback vertex, it means you want to identify a set of vertices whose removal destroys all the cycles. So how does it relate to the vertex cover? That is the question.
and we do not want to lose connectivity. We only want to lose cycles present in the graph, is it? And we
No, no,
want
no.
to maintain
Connectivity
the
can be
connectivity.
lost. Connectivity can be lost. There could be multiple trees. That is also allowed.
Okay, okay. So, can you repeat I mean, this meaning of FVS? We need to find the largest set of the vertices, or what? I
Minimum.
mean,
So the definition is the following. Let us look at the definition. So feedback vertex set. So it is the minimum number of vertices or set of vertices, I'll say. Let's give you the exact. So because we are in the parameterized domain, we have as part of the input the parameter k as well. So the question is, does there exist a set X of at most k vertices of G such that removal of X, that means G minus X, is a forest?
okay.
So what is the relationship with vertex cover? That's what you were asking.
Yes, in vertex cover, we need to find the minimum set of the vertices covering all the edges, and here we need to find the minimum set of the vertices whose removal will destroy the graph and will convert this into a tree rather.
Yeah, I would destroy the cycles.
Cycles, yes. So once a cycle is destroyed, then graph will no longer be a graph, it will become a tree, is it?
No, so a tree is also a type of graph. So
Yes, yes,
it will no longer be a graph with a cycle. So it will be an
yes,
acyclic graph.
yes. Uh,
So I don't know whether explicitly these two things can be related. Uh, I will give it a thought and I will answer that next time. I cannot immediately
yes,
think of the relationship.
yes. Uh, at the most, I can recall of that Menger's theorem, which used to say that the number of the non-adjacent edges in between any two vertices is equal to the minimum number of the vertices required to be removed to separate those 2 points. Something. I mean, this is somewhat sounds similar to this thing, but uh, no, the relation between this and vertex cover. Yeah.
Okay, okay, Menger's theorem, all right. It is in a finite graph, the size of a minimum cut set is equal to the maximum number of disjoint paths that can be found between any pair of vertices.
Yes, this is
Oh,
the Menger's theorem. Yeah.
that is almost like the max flow min cut theorem. But the difference is that there is no source and there is no sink.
Yes.
Maybe I'll ask someone who might know. So yeah, let's move to the next question. Okay, so the next question is about branching. Again, video specific question. So there's a video, lecture video, and where the branching vector is defined, and the branching vector has three components, D1, D2, and D3. And there is a formula which can be used to find what is called the branching number. Okay. So if you know the formula, you can apply the formula and you can find the branching number from this branching vector. And if you don't know, then I'll tell you the formula. First, let's write down the question, at least the branching vector. So there are three components, the branching vector. Oh, do you want to read it? Maybe I'll give you some more time to read the question. The next question is not very video specific, but then we can discuss more the next question. But this one, you have to know the formula.
So this branching thing is useful for what? For getting the rules of the reduction. If we, because in the branching, I saw some of the videos and wherein we take an instance of or a particular branch of the given instance, and then we develop the recurrence relations. I mean to simplify the solution. But then can we find this branching for all the problems of kernelization?
Yeah, whenever you're relying on branching, so to identify that how much time we will require, what is the kind of pace of the exponent, you have to rely on this formula. So when you are branching, so you are taking either this branch or that branch, or there could be multiple branches, and then the computation is proceeding along that branch. So what I think, although I may be incorrect, that with this branching vector, if you calculate the branching number, that will sort of give you the base of the exponent. That is sort of helps you to give a bound on the running time for that branching algorithm.
Okay. Hmm.
So here is the formula. This is Q question 2. So your branching vector is T1 equals 2, T2 equals 2, and D3 equals 3. So you are interested in computing the branching number. There's only so much intuition I can give. So first you identify that what is the largest component in the vector. So what is the largest out of D1, D2, and D3? So that is 3 in this case. And then you construct what is called the characteristic polynomial. So the characteristic polynomial is the following. So it is lambda to the d minus lambda to the d minus d1 minus lambda to the d minus d2 minus lambda to the d minus d3. Now, if you set it, so this is the characteristic polynomial. If you set it to 0, then the positive root of this equation will be the branching number. Okay. So let us put the values. So set it to 0. So d is 3, d1 is 2, 3 minus 2, 3 minus 2, and d3 is 3. So this is what we have. So the polynomial, the equation becomes 2 lambda this thing. Now you have to find the positive root of this equation. That is your corresponding branching number.
So, you know, so if I put the value of lambda is equal to 1 here, that will not satisfy this. If I put 2 here, then 8 minus 4, no, minus 1.
Yeah, so let's first do one thing. Let's try
Minus 1. If I try minus 1, then minus 1 plus 2 and then minus 1. Yes, so for lambda is equal to minus 1, I got this. Yeah, this equation satisfied.
okay, so let's minus 1 is correct. So let us say we'll try to factor out lambda plus 1. So plus lambda square minus lambda square minus lambda minus lambda minus 1. So we factor out lambda plus 1. So take lambda square common. So we have lambda plus 1. Again take minus lambda common. We have lambda plus 1. And take minus 1 common. Then we have lambda plus 1. So we have lambda plus 1 times a quadratic term. So this is what we have, and for the quadratic we can apply the Sridharacharya formula. So lambda turns out to be so minus b minus minus plus minus b plus minus uh, wait first give the this thing, minus b plus minus with over b square minus 4ab. Wait, what is it?
Minus
4ac
yes,
by
1 plus
2a.
minus root of 5 by 2.
So come again.
Yes, this is right. Yeah. 1 plus
Okay.
minus root of 5 by 2. Yeah.
Yeah, so there is only one positive root. So the positive root is unique and it is equal to 1 plus root over 5 by 2. This is our branching factor. So you can see that uh, this is how much is that? So root 5 is 2.24. So this is less than 2. So this number is less than 2. Yeah, I mean, so to give you some intuition, so it helps. So instead of saying something is 2 to the power something, you have reduced the base from 2 to something smaller than 2. And okay, so I'll think more about it. That what is the intuition behind the branching number? Not think, I'll find out. So this is the branching number that we are looking for. So let's look at the options. This yeah, option is saying 1 plus root 5 by 2 is the accepted answer.
Yes. So yeah, 1 plus root 5 by 2.
So next 4 questions are part of the same question. So 3, 4, 5, 6 are in fact related. So let you read the question for a few minutes, then we can discuss it. Okay, so I hope you have read the question. So we are solving the vertex cover problem, and at some intermediate, uh, so suppose that we have the following instance at an intermediate node. Okay, so we have this instance. So this instance is saying that does there exist a vertex cover of size 4? But instead of answering that question directly, we will take help from linear programming. So we will compute an optimum half integral solution. Okay, so what is an half integral solution? So recall the linear programming relaxation of the vertex cover problem. So let us first recall that LP. Then we will look at what is a half integral solution. So maybe we can copy this diagram before we move to the white. We'll copy this diagram. So here's a vertex cover instance, and what is the objective? So first of all, for every vertex, you have to consider a variable. For every vertex, we consider Boolean variable to start with. Okay, but I'll just say variable because we'll relax the 0 1ness. Now the objective is to minimize the sum of all these variables subject to for every edge. So what is the meaning of vertex cover? For every edge, you have to pick at least one of the endpoints. So for all uh, edge, let us say u comma v, you want to take at least one of u or v. So xu plus xv should be at least one. Okay, and if we relax, then xu and xv are taken from the interval 0 comma 1. If we do not relax, if we insist on Boolean values, then you have to take either 0 or 1. You have to take either 0 or 1 for every variable. But if we relax, then we are saying that I can also allow you to take fractional values between 0 and 1. That is the LP relaxation.
So I have a doubt here that if the only Boolean values are permissible for XU and XV, then this won't be an instance of linear programming, and this will become the case of the integer programming rather. Uh,
Yes.
yes, so because the ideas of LP can be applied if we allow continuous values for XU and XV.
That is why we will relax and we will say that the interval is continuous, and you take a value. So if you say that, okay, for this vertex, I am assigning a value of 0.373, then I will accept it.
Okay, okay.
So ideally, if you take values 0 and 1, then you are clear that whether you are taking a vertex into the vertex cover or not. For example, if you're taking D, then the Boolean variable 1 is indicating the fact that you have taken D. Similarly, if you set C to 0, that means you're not taking C. But if you say that I have a fractional value corresponding to one vertex, then it is not clear what you are doing. Then we have to do one more step called rounding. That we have to either set it to 0 or 1, and then we have to argue that how far we are from the optimal vertex cover.
Okay, okay.
So there's a term in the question which is beyond what we discussed. Says that so we compute an optimum half integral solution. So look at the solution. Xa equals xp equals xc, and means everything is set to half. So half integral means you are allowing 0, 1, and half, but no fraction between 0 and half, no fraction between half and 1. You allow only three values. In that case, the solution is called the half integral solution. Okay, so let's write it down. So half integral solution means every variable, okay, can take value 0, half, or 1. That's all. Now, with that constraint, you can still minimize this sum. So they're saying that for this instance, that means this graph, if you set every variable corresponding to each of these 6 vertices to half, that will minimize the sum of the variables. So let's write down. So they are saying that for this particular graph, they are setting everything to half. So they're saying that okay, xi is half, xb is also half, xc is also half, xd is also half, xe is also half, xf is also half. They're saying that with this assignment, this summation is minimized. So what does this 6 terms together sum together give? 3. So they're saying that okay, if you have to minimize this function, then somebody cannot get better than 3, even if uh, uh, they're allowed to take values from this domain. Okay. So
And
they
what's the
found
mean?
this. Yeah, go ahead.
Then what's the meaning of taking the value of one vertex as half, like say xc is half and then xf is half?
You mean what is the physical meaning?
Yes.
So at this point, there is no physical meaning, but there are more steps. The first step is to obtain the optimum half integral solution. That is the first step.
Okay. Okay.
So after that, they have the second step. So now they're saying that identify that vertex, if at all, for which this so, so identify a vertex such that if you remove that vertex, if you take g minus v and then run your half integral algorithm, then you will get some other value of the half integral solution. So they are removing a. They're saying we compute an optimum half integral solution for LPVC g minus a. And they said, okay, once we have removed a, in this figure, removal of a means the two edges incident to a are also removed. So now there is no obligation to cover the two edges AC and AB once A is removed. So therefore they're
Yes.
saying yes. So therefore they're saying that after the removal of A, the best, the minimum half integral solution is setting xp to 0, because even if you set xp to 0 and x is not there, you have no obligation to cover AB anyway. So the rest of the vertices you set to half. So now this solution, some of these variables is half into 4, 2. So now they have identified a vertex for which the half integral vertex covered is one less than what it was before the removal of A. So they have identified a special vertex, that is their agenda. That okay, we can identify a vertex whose removal reduces the half integral solution by exactly 1. So that is what they're saying. Note that VC star G minus A plus 1 is VC star original graph. So this gives us the following not at all half optimum uh, half integral solution. Okay, so now they're reintroducing A, that okay, so we have this solution. Now we can reintroduce A and we can set Xa to 1. And this is a solution to my vertex cover problem. Okay, so now the question is, using this solution, uh, what are the reduced instances? Okay, so it's slightly video specific, but so far what we have discussed is not video specific. So now consider this solution. You have reintroduced A and you are setting A to 1 and B to 0, and rest of the vertices are half. So now at this point, the reduction says that you get rid of all the vertices which are either set to 1 or set to 0, because for them you have made a decision that the vertex that you have chosen is set to 1 and the vertex that you have not chosen is set to 0. So you can, for now, you can stop worrying about them. So that is the reduction step. You don't worry about them. So after you get rid of these two vertices, you are left with 4 vertices only. Okay. So option C and D are immediately discardable. Now we have to make a decision between option A and B. So far, so good.
Yes.
Okay.
And
So now,
what this k here is, k is equal to 1 and k is equal to 3.
so K is the size of the vertex covered. So now, how many variables you have set to 1? Only one variable you have set to 1. So you have the liberty. So you started with K equal to 4. Now one variable you have included in your vertex cover. Now you have the liberty to take uh, 3 more vertices into the vertex cover. So K equals 4 to 3. Like 1 you have taken, you can take 3 more. So now therefore K is reduced from 4 to 3. So therefore B is the correct answer.
Yes.
Okay, so this is like saying that okay, after we have done reduction with the help of the LP, what is the reduced graph? So this is the reduced graph along with the reduced parameter.
So
All
not
right.
only this, not only this, there could have been many more heuristics. Like say here they have used one heuristic that okay, we need to find one such vertex such that its removal will bring the vertex cover in that format. We just
Yes.
need to add +1. So there could be other heuristics as well, and which could be better than this one.
Better in the
And
sense running time.
better, yeah, so better in the sense that here we have reduced, say, the value of k by 1, just 1. So from 4 to 3, and there could have been heuristics, say, using them, we could reduce the value of k by half, say, or by some reasonable good amount.
Yes. So you're saying that you could have made faster progress using some other heuristic. That's what you're saying.
Yes, yes, yes.
Yeah. So when we measure progress, we measure it in terms of running time. And I think as far as this LP based thing is concerned, uh, this was probably the best they could do. But you are right. If somebody designs something which is significantly different from their heuristic, then one might do better.
Okay, okay. Yeah. And certainly this is different from the approximation algorithms. I mean, this strategy is different from the approximation algorithms, is it?
So approximation algorithm for vertex cover is like better than 2 is not possible. So 2 approx is the best we can do. Okay.
Mhm,
But
mhm.
whereas here they're going to find uh, exact vertex cover, but the running time will blow up. But with the approximation algorithm for vertex cover, you can get a very fast 2 approximation. That okay, I am 2 factor away, but running time is reasonably fast.
Okay, okay.
Two different paradigms. Here the running time will be worse, much worse, but they will get
Mhm.
something as I said, 2 to the power k and then n to the power constant.
Yes.
So you are right. So approximation algorithm paradigm is completely different from what they are doing here. So, but for vertex over this problem, a better than 2 approximation will not be possible. So this is 7 o'clock now. We can take a short break, and I think I will keep this open for you. You can read the next questions, which are similar, and 4, 5, 6. So let us take how much break shall we take?
Um, 10 minutes at
Okay,
least.
7:15 also we can come back. Yeah.
Yes, yes. Thanks, thanks.
All
सात 15 उसे भी पता था कि आज सुन
Am I audible?
Yes, audible.
Okay. So yeah, these three questions are all related. In fact, uh, you can try to answer this question. So in question 3, that means in this question, we have this reduced graph. So coming from this larger graph, A and B are deleted, and we have this reduced graph, which is again 4 vertices, C, D, E, F. Now the question is that what is the change in K minus the vertex cover half integral solution? Uh, yeah, so what was the K before? K was 4, and the vertex cover half integral solution was 6 times half.
Yes, it was 3.
Yes. So now the K has reduced from 4 to 3. And what is the change in the vertex covered half integral solution? So half into 4. 4 vertices are left. Everybody gets half. So that change is also 3 to 2. So K minus Vc star does not drop. In the previous graph, it was 4 minus 3, that is 1. In this graph, it is 3 minus 2, that is again 1. So 1 to 1, 0 drop.
Yes, and this is for the question number 3. So in the question number 3 above, uh, so the value of K originally was 4, and it is dropped by what? It is dropped by, in this problem only. So there should be 1, I think.
Yeah, so K is dropping from 4 to 3.
Yes.
But Vc star is also dropping from 3 to 2, because earlier half into 6 was the value of Vc star, because there were 6 vertices in the previous graph. So now there are only 4 vertices in this graph. So Vc star is only 4 into half, that is 2. So the quantity K minus Vc star is not changing.
Hmm.
So that is why the answer is 0. Again, consider this instance. Okay, so now continuing the heuristic. So the first heuristic was okay. So you solve this LP half integrally, and you try to identify a vertex for which you can make a decision whether to include it. To do so, you have to check this criteria whether Vc star of G minus V is exactly 1 less than Vc star of G. So after you have reduced that graph to this graph, again you do this criteria check, and then you will realize that they are saying that we check if there is a vertex V in the graph such that Vc star of G minus V plus 1 is exactly Vc star G, but then we find that no such vertex exists. So at this point, I have this half integral formula, and I realize that even if I delete one vertex, this equality cannot be maintained. So why is that? And that is the question. So let us see. Oh, this one is doing branching. Okay, so this one is not why is that, but so now it's just saying that okay, now that no more we can make decisions about taking or not taking these 4 vertices, what shall we do? So next they will do what is called branching. So they're saying we branch on a vertex of degree at least 3. So now all the vertices have degree 3. So they arbitrarily choose D. Now if they're taking D into the vertex cover, then they cannot take any of its neighbors. So C, E, and F cannot be taken. But if they don't take D into the vertex cover, then the neighbors have to be taken because all the edges incident to D must be covered.
Yes.
So that's what they're saying, that what are the two instances that we'll get after doing this branching step. So one instance is corresponding to taking D, and the other instance is corresponding to taking the neighbors of D. So if you take
Yes.
D, then K decreases by 1 because you have included one vertex into the vertex cover. And if you take the neighbors of D, then the K value will decrease by 3 because there are three neighbors of D that you are taking.
Yes. 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 So definitely C is one of the answer. Uh, and C is the answer when we do consider D and the value of K is reduced by 3. Uh, so vertex cover of the size 3. K is the vertex cover of the size 3 and it has nothing to do with the degree of the 3s, degree of the vertex D as such, I think. So, but if I take if I take the vertex D, then the value of K parameter will get decreased by 1 only. So
Yes,
therefore, A is the correct answer. And
correct.
next one uh, is there anything else to be found? Uh,
Yeah. So
and so,
other is corresponding to taking the neighbors. So
yes,
if you take the neighbors, then you are covering all the edges incident to the neighbors. Then you remove them. Then you are getting the reduced graph. What is that graph?
so yeah. So if I can you scroll it down? Probably the answer would be there at the end. Uh, oh, K is equal to 1 if I do not take anything. So if I take D, then yeah, so K is equal to 0 because a single vertex is remaining. And so the A and B are the answers.
Yes, yes, yes. So one is corresponding to taking D and
Uh,
reducing K by 1. And the other is
yes.
corresponding to taking the three neighbors of D and
Uh,
reduce K by 3.
yes. Yes.
So continuing on the same line, yeah, now they're questioning that, okay, so now when we were at this stage, when our reduced graph consisted of this graph, PDEF forming a clique. So at this point, we could not apply this LP heuristic, this reduction rule, because the reduction in this quantity. So now you will read the question. So the measure. Now I'm looking at question number 6. So in question 5, the measure K minus VC star of G dropped by how much along the two branches? Okay, so now consider the two branches only. One branch is empty graph, the other branch is C, E, and F.
Yes. So if we take the first branch as CEF, because it's because of the option A. So then this is so K minus VC star is dropped by 2 minus half, 2 minus 1 and half. So 2 minus 1 and half came out to be half.
Yes,
And if we
yes.
consider the second one, so then 2 minus 0, so half and 2 would be the answer, I think.
No, so consider the original graph. The original
Yes,
graph has original means after this reduction step, this is the graph. So K
yes.
is 3. Now you have
Mm-hmm.
branched on this graph.
Mm-hmm.
So after branching, you have these two subgraphs.
Mm-hmm.
So now K has reduced to 2 in the first one.
Hmm.
And VC star was 4 times half, that was 2, but now it is 3 times half.
Hmm.
So it has reduced to 3 by 2.
Hmm.
So
Hmm.
K minus VC star, let's do this on paper.
So 2 minus 1 point half, half is 1.
Yes, yes, that is true. So 2 minus 1.5, that is half. The other case is K was 2 And so 2 minus VC star, no, so K was 3 originally. So 3 minus 2 was K minus VC star, that is 1. Now K is 0. So 0 minus what is VC star? VC star is again 0 because there are no vertices to which you will put this half integral fractional values. So K minus VC
Yes.
star itself is 0. But before you did the branching, K minus VC star was 1. So after branching, K minus VC star is 0. So the drop is 1 minus 0.
Yes. Yes. So one is the answer.
Yes.
So half and one is the answer.
Yes.
Yes.
So far, so good. We have already taken care of 6 questions. In next 10 minutes or so, we should be done. So let's look at this question. So what is a odd cycle transversal? So similar thing. So we have seen that in feedback vertex set, we are asking that what is the minimum number of vertices we should delete so that all the cycles are destroyed. So here we are asking that what is the minimum number of vertices that we should delete such that the graph becomes bipartite. Let me check if I said the correct thing. Yes. So let me write it down. So what is a Watt cycle transversal? So question number 7. Odd cycle transversal. Again, you are given a graph and a parameter k. So the question is, does there exist a set X of at most k vertices of G such that G minus X, if you remove X from G, it becomes bipartite. So you can clearly define two bipartitions and the edges are going from one partition to the other. So we are insisting on obtaining a bipartite graph. So what is a bipartite graph? So there are two partitions and edges are only among one vertex from one part to another vertex on another part. So in each partition, the edges are not there. So each partition is an independent set. So this is an example of bipartite graph. All right.
Yes. Um, so is there any algorithm to check that whether the given graph is the bipartite one or not?
Yes. So you have to check whether there are. Let's look at that picture. So in a bipartite graph, there are no odd cycles. Okay. There could be even cycles. For example, let's in this figure, uh, you could have a situation like this, that there is an edge like this, then there was an edge like this, then there was an edge like this. This is a 4 cycle, but you cannot expect an odd cycle, 3 cycle, because of the way bipartite graph is defined, and therefore uh, it's also too colorable. So if you do one PFS starting from one vertex in a graph, then the tree that you get. No, I think you should do DFS. Just a second. Let's do DFS. So if you identify, not identify, so you have been given a graph, you want to check whether it is bipartite or not. So you start doing depth first traversal from any arbitrary vertex. So you will get a DFS tree. Okay. And then you won't have odd cycles. So if there are back edges, then you will check whether it's an odd cycle or not. If it's an odd cycle, then its graph is not bipartite. So you can check that whenever there is a back edge, whether the cycle is forming. So how much is the jump? If the jump is by 2 levels, then you have an odd cycle. If the jump is by 3 levels, then you have an even cycle. So you can keep track of the cycle length. Do you understand?
Yes, I got this point that if the graph is a bipartite one, then only even length cycles are possible.
Yes, and then you can check whether the graph contains odd length cycle or not by doing one DFS.
Okay, yes.
Let me be sure that if I said what I said is correct. How to check bipartiteness? Yeah, so they're saying that check if the graph is too colorable or not. So with BFS also it is possible to do so. So one algorithm is you do BFS. So assign red color to the source vertex and color the neighbors with blue, and you keep assigning alternately blue and red. So while assigning colors, if we find a neighbor which is colored with the same color as the current vertex, then the graph cannot be colored with two vertices. With two colors it should be. Okay. So
Yes.
I think with DFS also we can do it, but there is an algorithm with BFS.
Mhm. Yes.
Yeah.
What the question is? What are they asking that?
So this question, right? So this question is asking that consider this graph A, B, C, D, E, F, G. How many seven vertices are there? And the question is it possible to delete one vertex in this graph such that it becomes bipartite? So when you delete a graph, the vertices, sorry, when you delete a vertex, then the edges incident to that vertex are also deleted.
So I think that on the screen some other question is displayed because I see a different question here. Consider the following instance of the odd cycle traversal problem as discussed in the module 2, lecture 11. So
Yes,
I'm seeing this.
this is the question I'm showing, but yeah, so the question odd cycle traversal with this instance means that they're asking whether there is one vertex that can be deleted to destroy bipartiteness. Now, to answer that question, they have some machinery that is discussed in module 2, lecture 11.
Okay. Now I understood. Yeah.
So what they have done is from this graph, they have obtained a reduced graph. In fact, they've obtained a larger graph. They have made copies of each vertex. So for example, you can see A1 is there, A2 is also there, B1 is there, B2 is also there. So earlier you had seven vertices, and now you have so many vertices. Uh,
Double, just double off. I mean, twice of the number of the vertices. Figure is kept below and figure is kept above, and then all the vertices, then all the vertices of the below figure and the above figure have been connected through the edges.
Yes, correct. And the copies are also maintained. So for example, A is connected to B and C. So A1 is connected to B1 and C1, and A2 is connected to B2 and C2. So first copies, if you take only the first copies, then you get the original graph. If you take only the second copies, then also you get the original graph.
Yes,
And for every vertex, the first copy and second copy are also connected. A1 is connected to A2, C1 is connected to C2, and so on.
yes.
So you can think of one vertex as being so one making another copy of this graph, and then sort of uh, like connecting the two things. So what is n? N is the number of vertices in the original graph. So in this case, n is 7 and k is 1. So they're saying,
Uh, K is 1 means vertex cover of the size 1. Like if I only choose the vertex A in the vertex cover. No, no,
mhm.
no, that is not covering all the edges. So what this K is equal to 1 here signifies?
So k is equal to 1 is asking the question that can you delete one vertex from the graph G such that G minus this vertex, this reduced graph is bipartite.
Oh, yes. So K is a parameter kind of thing here.
Yes. So observe that this Y set of vertices A1, A2, B1, D1, F1, C2, E2, G2 is in fact a vertex cover for this G tilde, this larger graph containing two copies of every vertex of the original graph. And it contains n plus k number of vertices. So n is 7, k is 1. Now, from this observation that, okay, this Y is vertex cover for G tilde, your task is to obtain a k size that is one size OCT, that is odd cycle traversal of the original graph. So the way to do that is that uh, so remove from G tilde all the vertices in Y. Okay, so let me copy this and we'll do this. Or maybe I'll just say what it is. So you have this G tilde graph. You know Y is the vertex cover. So G tilde minus Y, I mean the rest of the vertices in G tilde, they will form an independent set because the
Yes,
complement of vertex cover is an independent set.
yes,
Okay, so how many vertices are there in G tilde? 2 times n because we have copied every vertex twice. So the
yes,
independent set size is 2n minus n minus k. That is n minus k.
yes,
Now, in this graph, sorry, in this independent set, let us note down the vertices that are in the independent set. And from the independent set, we will see that some vertices are appearing as first copy, that is A1, A2 like that. And some vertices are appearing as second copy. And some vertices are not appearing at all. So those vertices which are not appearing at all, that will be part of the OCT, that is odd cycle traversal. That is the algorithm. I will.
uh, s- yeah, yeah. So only 4 vertices are, so there are 10 vertices here in Y. So 4 vertices are not included.
10? No, no,
V2,
not 10, 8. N
3
plus k
and
size. N is 7, k is 1.
yes. So A1, A2 is there, and then B2 is not there. Oh yes. Oh yes. C1 and C2 both are not here. Yes. So
No, no,
3,
C2
4,
is there. C2 is there. C2 is there.
C2 is, oh, C2 is there. So then E1 is not there then.
Correct. So now in the
Yes.
independent set, what do we have? The rest of the vertices.
Yes.
Now there in the independent set, which vertex has not appeared at all?
Which vertex has not appeared at all means?
Okay, so I want to rephrase the question. So you have this vertex cover Y. So you know
Yes.
that its complement is an independent set.
Mhm.
Now in this independent set, if uh, if you can identify that none of the first or second copies of a vertex has appeared, such a vertex you can identify, then that vertex will be part of the odd cycle traversal. So in other words, in the vertex cover, if you can identify both copies of the same vertex in the original graph, then that vertex will be part of odd cycle traversal.
So like A1, A2 here is appearing.
Yes.
So
So that
so
means that neither A1 nor A2 can be part of the independent set. And that is the reason, as per the algorithm described in the video, A will be part of the odd cycle traversal. And you can also verify it from the figure that if you delete A and all the edges incident on A in the original graph, then what are you left with? You're left with some independent edges, B, C, D, and F, G. So you're left with a matching, and a matching is a bipartite graph. So you have, in fact, found a bipartite graph. You have uh, destroyed all odd cycles.
yes.
Far so good. This is last question. Yeah, so this is something that I will solve immediately. Like I will just look at the question. I will, even without watching the video, one can solve it. So let you read it. First of all, so what is almost two set? So almost two set means you are given a Boolean formula, which is two set. Okay, so two set means every clause has at most two variables, and
Yes.
almost two set with k equals to 1 means, can you uh, so it says that can you delete, let me be correct, uh, whether I'll tell you what is almost two set. Okay, so can you delete at most k clauses such that this Boolean formula becomes satisfied? So maybe this Boolean formula is not satisfiable, but deleting k clauses, can you make sure that this Boolean formula is satisfied? So in this case, phi has three clauses, y or x bar or y, and y bar. So can you delete exactly one of these three clauses such that the rest of the clauses can be satisfied with some assignment? So that is the question. Now, so from this almost two set, they construct a graph G phi in the video, and then they say that, okay, consider the k size, that is one sized variable set x, and note that if you delete x, Then what are you left with? All the clauses.
I have a question here that what is the, I mean, which vertex is there in this figure which is connecting to the complement of y?
X. Oh, this other guy. Okay, so one, you're saying that one of the vertices is not named. Why is that
So
so?
they have constructed this graph from this phi only, and rest of the connections are easy to see. X and X is connected to Y because of the first clause, and X bar is connected to Y because of the second clause. And then what's the reason behind connecting X complement to X is not clear. And similarly, Y and complement of Y is also not clear. And then to whom Y complement is connecting to is also is not given.
I agree. This vertex is not even named.
So how do they construct this G phi from the given formula phi?
Very good question. Are you able to hear the video when I play it?
So can you play it once? No. I mean, voice is. It's not audible to me, but I can see, but I cannot hear.
Welcome back to the final
Now
module
now
of the
it's
second
audible.
week on branching algorithms.
It's audible.
This time, we will be looking
Yes,
at
it's
some
audible.
applications of the algorithm that we developed in the previous lecture. And there are only so many boxes, so I suppose there are the same way that we solved OCD. We are going to build a graph based on this formula, and we're going to argue that this graph is a yes instance of vertex cover above matching.
Oh, it's a okay. I think there's something which is not matching with what is written in the textbook. So the textbook is saying that almost two set means the question we are asking is it possible to make phi satisfiable by deleting at most k clauses? But what she is saying in the video, can we delete at most k variables to make phi satisfiable? So instead of clauses, she is talking about deleting variables. So I
Okay.
don't know what is the truth.
Mhm.
So, but they have,
So
yeah, go ahead.
I have one more question here that why the captions are disabled, I mean, in the videos of this subject, and moreover the lecture slides are not available for download, and lecture notes, and which are
I also
available for
have the,
download.
yeah, I also have the same question that why these PPTs are not available. Then I wrote to NPTEL. They said that the instructors have to make it available, so they don't have it. So if you write to the instructors, I think you might get it. But ideally, it should have been made available. I don't also have it.
Okay, yeah.
So you can either write to Saket Saurabh or Nildhara Mishra. I think these are very helpful. Instead of going through the entire video, if you just look at the lecture notes, it's much more helpful.
Yes, and moreover the captions are also disabled here, because even if I view the videos at the speed of 0.75, but because of the fast speed
You
of
can only use the
the
Yeah, I can see the
communication.
captions. Here are the
so
captions.
How come, but not coming in my place? Okay,
You have to just click on CC, that is subtitles. It is turned off for you.
I did that. I will do it again. Yeah, thanks.
Yeah.
first in
But I think that what she's saying, the way they have defined the problem, almost to set, is not consistent with what is written in the textbook. So I will ask what is the truth. So we can park this question for later discussion. I don't know,
Yes.
there's some issue. I also, I think I should have found this out before, but yeah, I mean, I take the responsibility, but we will discuss it next time. So if you just worry about nothing but the question is asking, can you give us n plus k sized vertex cover for this graph? So what is n? Number of vertices, variables in the Boolean formula. So only two, x and y, two variables are there, and k is said to be one. So you are asking for a three-sized vertex cover for this graph, and then you can identify the answer from the possible options.
Yes. So it is. If I include x and then the complement of x, then yeah, this everything is covered, and I need to include y complement of y. So A is the right answer. X, I need x and then the complement of x and then the complement of y.
Yes, but this graph is not well defined, as you have pointed out. One of the vertices is not even named, and the problem itself is not, the definition itself is in the video is not matching with in the textbook. So you can also try to find it out. I will also try to find it out.
Yes, and moreover, this two set is solvable in the polynomial time. So is this almost two set is NP hard or what? And therefore we are trying to reduce it into a vertex cover kind of thing.
That is also true. So if you're saying that, why are you even bothered to delete anything?
Yes, yes, because two set we can solve it in the polynomial time. And moreover, the construction is somewhat similar to this construction while proving that two set is solvable in P. Uh, so we take variables and then their complements, and then we connect the edges.
So the question that we are asking, that can we delete at most k clauses such that the two set formula becomes satisfiable? So that is always true. Yes, means you don't even need to delete any clauses. It will always be satisfiable. That's what I was saying. But so how about, so x or x bar if you have can you, okay, so what is the two set question? Just let me verify. So any two set formula is satisfiable. That's what you're saying.
Yes, yes, two set is yeah solvable in polytime. So almost meaning of almost could be uh,
Okay. So I have to so I don't know what is the meaning of almost two sets. So what is written in the textbook is you're given a CNF formula 5, where every clause consists of at most two literals and an integer k is also given to you. Question they're asking, is it possible to make this Boolean formula satisfiable by deleting at most k clauses? That is the definition of almost two set in this book. I don't know. I will try to find out that what is the context in which we are solving this almost two set this way.
Yes. Yeah.
Thanks for pointing out. It was something that
Yes. Yes. Because
I
this
overlooked.
is yeah, this is somewhat similar to that. The one problem which we but then that problem was different, which we solved in the complex computational complexity problem solving session, but that was exact two set problem. So this is almost two set, and that was no, that was double satisfiability problem. That there
Double
should be
satisfiability means how many literals per clause?
no. The meaning of the double set was that it was an instance of the satisfiability problem only, but then we should have at least two solutions, two assignments, two satisfiabilities.
Okay, so there should be two different satisfying assignments.
Yes, 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 yes. So that was different from this one because that was a normal satisfiability problem, and this is a two set. Yeah.
Okay. All right, so this is the end of today's session. So we'll decide on the regular slot and we'll shift it to another day from Tuesday, and I will inform you.
Sure. Thank you so much. And can you please share these notes somewhere like previous time in the Google
Oh,
Keep?
yes, 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 I'll do that. Okay, so
Thank you so much.
thanks
Thank
a
you
lot.
very much.
Good night. Take care.